Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over what's known as multi-step synthesis. This is the last section of this chapter. Now, it's very important that you built everything up to now and you feel comfortable with the sections leading up to this particular section, because this is kind of like the wrap up, but it is much easier to learn if you really have a good understanding of everything that led up to this point, okay? Because what we're going to do in this section is nothing new. We're just going to combine reactions that we've now learned about, and we're going to see a whole bunch of different ways that we can combine them to get different products. And what makes this challenging is when you're looking at a product and you have to figure out what to do to get there. It's not so simple if you're not comfortable with the basic reactions, okay? So before you continue with this video, make sure that you feel comfortable with alkylation, hydrolysis, decarboxylation. These are very important topics. Okay? Not so much halogenation or deuterium exchange. That's not important. Alkylation, hydrolysis, decarboxylation. Hydrolysis is when we turn an ester into a carboxylic acid. Okay? And we do that by base, and then we follow up with acid. Okay. Now, so let's get started. So there are three sections here. The first two are just standard templates that we learned from. It's like we have to begin somewhere, and these are two that we learn as a base to begin with. And then we expand beyond that into other possible scenarios. And that's number 3. Okay, let's get started with number 1. So as you can see, I already typed this out because I want you to be clear. These are the 3 things that we're always going to do with the molecule I'm about to show you. We're going to alkylate up to 2 times. Up to 2 times. Remember that you could do it twice, and it doesn't have to be the same alkyl group. Number 2, hydrolysis will turn esters into carboxylic acids. And number 3, we're going to get rid of the carboxylic acid, decarboxylate. Okay, now the acetoacetic ester is this right here. This is known as an acetoacetic ester. Now this could be R. Right here is R, and it could be ethyl, it could be methyl. It really doesn't matter what that is. I'll write ethyl, but I just want you to realize it doesn't matter. Whatever R group this is fine. Okay, so it just has to be an ester. So this right here is called an acetoacetic ester, and I'll show you how the name comes about. So what we have is, obviously we have an ester. You could see that, right? Now we have an aceto group. Right here is an aceto, right? An acete, like acetone, right? Imagine if this didn't exist, if I erased all this, that's acetone, right? So that's an acete group. And then over here's another acete, to the ester, right? So you notice how the ester has a methyl next to it if you erased this right here. So that's an acete group, right? For the ester. Sorry. Come on. Oh, I guess it's just locked together. Anyway, the ester is on the left side of it. This red carbon is a methyl if it wasn't for the ketone, right? So we call it an acetoacetic ester. You have to be you have to be familiar with this. I wonder why it's doing that. Okay, there you go. So you have to be familiar with this molecule because this is what you begin with. Now it turns out that when you do these 3 things, the end result is that you make a methyl ketone. This is the key. We make a methyl ketone. So let me show you how this works. Let me give you the mechanism. And I want you to recognize that what we're going to do, and let me just I want you to visualize this. Everything that we're about to do is, between those 3 steps, is to modify initially this red alpha carbon. Remember, that's the most acidic carbon, right? So if we use a base, we're going to lose an H there. Notice how many H's it has. It has 2 H's, right? So we can alkylate up to 2 times. See that? Because we could pull off an H and put in an alkyl group. So once we do that, once we put an alkyl group up to 1 or 2 times, then we're going to turn this into an ester, into a carboxylic acid, and then we're going to make it disappear. And notice that if we do that, if I erase this right here, notice that I'm left with a methyl ketone. See that? So that's why we make methyl ketones. This is all I'm going to show you right now. That's it. What I just explained is what we're about to see. So the template goes like this. We start with our acetoacetic ester, and what we do is whatever this is the base that we use. So if there's an OET, then we write OET minus. If it was OME, OME minus, right? You always use the base that you have as an ester, because here's the idea. You don't want this to come in here, because it could do that and change the ester, because that's not going to help us for our goal. So if we have the same exact group there over the arrow that's already the ester, it won't do that, because it's just going to make the same thing over and over again. And so that's why we use that as the base. So we always pick whatever the ester is, okay, as the base. Now, it doesn't mean, by the way, on a test that they won't change that, because sometimes they do. They don't follow the rules just to make it more tricky, but we'll get to that, you know, when we go through old exams. But this is how we would do it anytime, and this is usually how it should be done. Okay, now, so what's going to happen is we're going to pull off an H. We're going to deprotonate the carbon in the middle. Now remember, this carbon in the middle is acidic compared to the left side, right? The alpha carbon on the left, because this one in the middle has 2 carbonyls, beta, right? Okay, now we're going to do our SN2 reaction. Now here's the key. Unlike alkylation, where it's just a mono ketone or a mono carbonyl, this one can do methyl, it could do primary and secondary, as well as allyl. Look at that. So we added secondary to our list. So if it was a monoalkylation, like we did earlier, then you could only do methyl primary allyl. But because this is less basic, this carbon here is not as basic, it's more stable than a mono alpha anion, this one is not going to do E2 with secondary. So it's not as basic, and therefore it's a little bit better at doing the nucleophilic stuff, the SN2 that we needed to do. Okay, so you have to remember that secondary is allowed. Okay, and that's only if it's a dicarbonyl, a beta dicarbonyl, like acetoacetic ester. Okay, all right, so what we're going to do is we're going to add some kind of R group. Let's say we have, I'll make it generic. So let's say we have an R, Br, okay, where R equals one of these right there. Well, after this, we're going to get an R group attached on, right? So it's SN2, R comes in, and that's all we do so far. Now, we can repeat this again. We can add a new R. Remember, we could do this up to 2 times. See that? So we can repeat the same steps if we wanted to. Or, if we don't want to, we can repeat. And the key here, actually, let me make this also clear. I'll repeat again. I'll do another example. Is that we can actually do this with a different R group. So it's not like Grignard where it has to be the same thing twice if it comes in twice. Remember with class 2? Like a ester, for example, or an acyl halide, 2 times something comes in, the same thing. Well, in this case, it could be very different. So we can do another, number 1, OET minus, or NaOET. Number 2, we could do RBr. And this R could be completely different than the first one, because we're actually doing this step by step. We're actually changing the environment in order to get this accomplished. So these two are completely different. They could be the same. It's up to you. We'll learn about that in a moment. Well, once you're done, the next step is hydrolysis, right? So now we're going to do hydrolysis. Now there's 2 ways to do hydrolysis, but the one that we tend to do, and I already explained this to you before, but I'll explain it again, is we usually go sodium hydroxide and water to begin. And then step 2 is H+. Now, the reason why we do it this way is because we don't want to turn this into an acid environment. So we don't want to write H plus H2O. And you'll say, well, why am I mentioning this? Well, let me show you what happens. So if I do hydrolysis on the base, do you remember that the ester becomes a carboxylic acid, but in the base form, right? So this right here becomes O-. Now, we don't want an O-. We want that to be OH. So the next step is to write H+. And now we have an OH here. Okay? So that's right here what we do. Now, the thing is that we could have gone from here and skipped this part here and just wrote H+, and we would go right to the end. So we wouldn't have had to draw this one out. And now usually we couple this one with this one over one arrow. But I want you to realize that sodium hydroxide is initially first used and then H plus rather than H plus directly. So people usually say why?